Okay. All right. Good evening, everyone. So we are recording now, and let's see where we stopped last time. We stopped at a question. In fact, you were supposed to find an example. It was one of the try it yourself problems. Um, so, is it possible for two bridges to overlap but to not be skew? Right. So, any thoughts?
Yes, sir. Means
Yeah.
if let us means we showed that if they are we are first assuming that B1 and B2 are not skew, then the number of vertices of attachment for each of them must be greater than two.
Yes.
So assuming that they have both exactly three vertices of attachment,
Mm-hmm.
and if all three of the means three vertices of attachment of B1 are same as the three vertices of B2,
Mm-hmm.
then we get two
Exactly.
bridges which aren't skew but are overlapping.
Exactly, exactly. So that is indeed the only scenario where you can have two bridges that are overlapping but yet not be skew with each other. Okay? So the only scenario, and we'll prove it, is you have a cycle and you have two bridges with exactly three vertices of attachment and both of them having exactly the same three vertices of attachment. Okay? And we'll introduce some terminology. Two bridges.
Sir, I have a question.
Yeah.
So in this example, one is an internal bridge and the other is an external bridge.
Well, I've drawn it that way, but the point I made does not have anything to do with the drawing, right? Yeah.
Yeah, that I know because those
Okay.
are graph invariant concept, but I am
Okay.
not means getting why they are not overlapping.
What is the why they are no, they are overlapping. So
No,
the
no, they are
point
overlapping,
is
but why they are overlapping that I am not getting.
why they are overlapping. What is the
Yes.
definition of overlapping? Can you tell me the definition of overlapping?
Definition of overlapping means okay, so all the three vertices of so suppose if indeed B1 and B2 does not overlap, that means they avoid each other. In that case,
Right.
all the three vertices of attachment of B2 will be contained in exactly one of the three segments.
Exactly. Is that happening here?
No, no, no.
Exactly. So because
Hmm.
they are not avoiding, they are overlapping. That was our definition, right? And you just check that they are not avoiding each other, right? And therefore they are overlapping.
But they are not skew.
They are not skew because we don't even have a total of four vertices of attachment in total for B1 and B2,
Okay, 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 okay. Yes, sir. Yes.
right? Okay. So they are
Actually,
overlapping.
I thought about this, but this condition means this case actually ran out of my mind.
Okay, right.
Yeah. Yeah,
Okay.
because
So,
basically the
mhm,
entire concept of skew is defined for only when we have at least four vertices of attachment.
exactly.
Because here we
Exactly.
have exactly three vertices of attachment, B1 union B2. So that's
Yeah.
why they
Yeah.
cannot be skew.
Exactly. So two bridges are equivalent if they have precisely the same set of vertices of attachment. If vertices of attachment of B1 is exactly the same as the vertices of attachment of B2.
So do you mean number of vertices or as a
No,
set?
I mean as sets.
As sets. So
Yeah,
basically set of vertices of attachment of B1 equal to set of vertices of attachment of B2.
yeah, same sets.
Okay. Same sets, right?
Right. Yeah. Okay. Good. And we will say that a bridge is a K bridge if it has exactly K vertices of attachment.
So in our example, both B1 and B2, there are three bridges.
Yes. So we have the case of B1 and B2. They are equivalent three bridges.
Yeah, yeah. Remember, they're equivalent three pages here.
And that is the only case when you can have the situation that they are overlapping but they are not skew. Okay?
So basically, sir, for two bridges B1 and B2 to overlap but not
Mm.
to be skew, they
Mm.
must be equivalent three bridges.
Right.
They must be equivalent three bridges. Okay.
Yeah.
But why that is the only case means is there any
We
other
will
proof?
prove it.
We'll prove it.
Yeah.
Okay, 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 fine.
Okay. In fact, it's not difficult to prove. So you can already start thinking about it on the side if you want to.
Okay.
Okay. So this is the only other scenario. But before we prove this, can we look at two examples? Can somebody tell me an example of a graph that we are kind of familiar with, where you get equivalent three bridges?
Means you want to mean there will be exactly two equivalent three bridges.
Yes, yes. I want a graph where there is exactly one cycle, and that cycle, I mean, there is a specific cycle, and with respect to that cycle, we have exactly two equivalent three bridges. In fact, what is the smallest example? Can you make the smallest example of a cycle with two equivalent three bridges?
So I can take a triangle as a cycle,
Good. And
and since the smallest bridge,
right.
which must have exactly three vertices of attachment, must be okay. Yeah,
Must
yeah,
be
yeah,
a
exactly,
K1,
exactly.
right? Because you have three vertices of attachment, it can't be a trivial bridge. It can't be a trivial one, right? Because trivial bridge will have at most two vertices of attachment. So you must have exactly three vertices of attachment. And what is this graph? Can somebody tell me what this graph is?
So I think it
K5
is.
minus 1 edge.
K5 minus 1 edge. So K5 minus 1 edge is the smallest example of two equivalent three bridges. Okay. What about skew? Can someone give me the smallest example of two bridges that are skew? Is it the smallest? Yeah, maybe it's not
I
going to
think
be
we
the
can take a
smallest.
four cycle and then start,
Right, right, right. So you can take a four cycle.
because there should be at least four vertices of attachment. That's why.
Okay. And now what should I do?
So I will keep a vertex. Suppose the vertex of cycle we are one, two, three, four in that order.
Hmm.
So
Hmm.
so one vertex will be diagonal, will be adjacent to the
K4 will be
diagonal.
enough, right?
K4. Did you say K4?
Yeah, K4 is satisfying.
That's right. K4 is actually satisfying. That is right. Okay. So that is K4. But I want to give you one more example, and I thought it would be the smallest one, but apparently it is not the smallest example. I will subdivide these two edges.
No, but sir, I have a question. So how
Yeah.
it works for K4?
Well, you take this cycle, C, your four cycle, one, two,
Yeah,
three, four, and
yeah.
now you have two bridges, one, two, three, and two to four. They are trivial bridges, right?
Okay.
Right? So they are
Okay.
two skew bridges. This
Okay,
is
but sir,
B1.
we define means the vertex. In any bridge, there should be a vertex which does not belong to the cycle.
No,
So
that is
the
not true. Those are non trivial bridges. We also discussed trivial bridges.
okay, so okay, okay, okay.
These are
So
trivial
a
bridges.
cycle
Yeah.
edge, an edge of a cycle can be a trivial bridge.
This is not an edge of the cycle. The cycle is this cycle 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So these edges 1, 3, and 2, 4 are not in the cycle. The cycle is a set of edges,
Yeah.
right? We discussed trivial bridges. They are
Okay.
also called chords of the cycle.
Okay. Okay. So basically, the edges one, three, and two, four, they are trivial bridges.
They are trivial bridges and they are skew with each other, right?
Yeah, skew. Yeah. Yeah. Yes, yes, yes.
But another example is you subdivide each of them by exactly one vertex. And what is this graph?
K5 minus.
No, it is
This
not
is
K5.
K33, right?
K3 minus 1 edge.
Yeah.
Okay. And this is K4. So this is an example of equivalent three bridges, which is one B1 and B2, the vertex and the three edges incident with it, right? And these are two examples of skew bridges. Okay. And this kind of explains this. This gives you another way of looking at why K5 and K33 are non-planar, right? You just cannot add that last edge to preserve planarity because one bridge is drawn inside, one bridge is drawn outside, and now you just cannot add an edge without destroying planarity between those two vertices.
Sir,
Yeah. Mhm.
this is a bit unrelated, but I had a doubt.
Yeah.
So, can we form like a further notion of planarity, like uh, two edges can at most intersect at one place or something like that?
Yes. Yes.
Like they won't be planar, of course, but
Right. So what you are referring to is a research area called crossing numbers. So crossing
I
numbers
think
is
there is a bound on the crossing number of k due to a dosh.
yeah, yeah, perhaps. But there's also some conjectures related to Turan about crossing numbers. So maybe Erdős's work is related to Turan's conjectures.
Means basically Edos gave an upper bound on crossing number of k,
Oh, I
something like
see.
that.
Okay, okay, that's interesting. I wasn't
And
aware of
I
that.
think that is means still to the best possible upper bound.
Oh, I see. Okay, right. Okay, so I am not familiar with research in this area, right? But the particular area you're mentioning is called crossing numbers.
oh, okay,
So the
okay.
crossing number of a graph, I won't write down these things, I'll just say it, is the minimum number of edge crossings among all the embeddings of that graph in the plane, right? And planar graphs are exactly graphs with crossing number 0.
Okay, okay.
So yeah, planar graphs are exactly the graphs with crossing number 0. Okay. And as you can see in these drawings, K5 and K33, the crossing number is exactly 1. Right? So K5, K33, the crossing number is equal to 1. And you can try an exercise to show that the Peterson graph, so this is a try it yourself, the Peterson graph has crossing number equal to 2. Okay.
So
So
basically, sir, in order to show that crossing number is 2, first you have to show that it cannot be drawn in a plane. First of all, Peterson graph is non-planar that we have shown.
yeah,
So its crossing number must be at least 1. So
yes,
if you can show that there exists no embedding such that
yeah,
there is exactly one crossing and there is an embedding where there is exactly two crossings, then we'll be done.
yes, exactly. So maybe I just wrote down. Okay. So the crossing number CR of G is the minimum number of crossings among all embeddings of G in the plane. Okay. And it's a vibrant, I mean, I don't know how vibrant right now, but in general, it is a research area with lots of open problems, many of them quite hard. So I don't know how active the area is right now, but I do know people who work in this area, and there is a lot of difficult conjectures, and even making small progress is fairly non-trivial. Unlike the case of planar graphs, where we actually know a lot more. Okay.
Okay.
So check out some works by Turan, and as Aranya mentioned, maybe Erdős has also some work. You can check out the progress made by Turan and Erdős. I think Turan has some very interesting conjectures. Yeah, good. All right. So Now let's prove what we have been saying for a while now. Let me write down the statement.
So I
So
can see that the conjecture of Turan is basically means just relates the crossing number of a graph and with the crossing number of its complement graph, G bar, something like that.
maybe I know of something related to complete bipartite graphs. So I think Turan was a fairly prolific guy despite being in the jail. Very interesting history. Uh, but yeah, he has a few conjectures also. I think it's called the brick factory problem, if I'm not mistaken. He was working in a brick factory because he was forced to work in a brick factory. These were very dark times. And during that work, he had some mathematical conjecture about which he called the brick factory problem. So we'll prove the following: overlapping bridges are either skew or else equivalent three bridges. Okay. So let's say we have a cycle C, we have B1 and B2, two bridges of the cycle which are overlapping. Okay, good. So what does overlapping mean? Overlapping means that they don't avoid each other. And let's go back to the definition of avoid. Um, yeah. So to avoid means all the vertices of attachment of one of them lie on a single segment of the cycle induced by the other bridge. Okay. And in particular, the bridges will have at least two vertices of attachment, because if one of the bridge has a single vertex of attachment, then there is only one segment, which is the whole cycle, and all the vertices of attachment of the other bridge will necessarily lie on that cycle. Okay. So clearly, they have at least two vertices of attachment. Each of them has at least two vertices of attachment. Otherwise, they avoid each other, which is the opposite of overlapping. Okay. So now suppose that suppose that one of them has exactly two vertices of attachment. Supposing this is my bridge B1 and it has precisely two vertices of attachment, U and V. Okay. Sorry, my display has disconnected. Give me a second. Okay. Yeah, it's a new setup, so I'm struggling with it. All right. So in this case, notice that all the vertices of attachment of B2, if they all lie on one segment, then they are avoiding. So that can't be the case. So because they are overlapping, B2 must have one vertex of attachment on this side and another vertex of attachment on this side. Right? Otherwise, they would be avoiding. And now, if you look at these four vertices of B1 and B2, you see that B1 and B2 are skew. Okay. So if one of them,
So basically both must have at least three.
yes, say B1 has precisely two vertices of attachment, then clearly they are skew. And I will just point you to this figure and complete the argument yourself. Okay, I won't write down the whole argument. All right. So now suppose that each of them has at least 3 vertices of attachment. Okay.
Sir, in that
Yeah.
case, we can show that if some block means if some bridge has at least 4 vertices of attachment,
Hmm.
then so suppose B1 and B2 we have 2 bridges.
Hmm.
If both have at least 3 vertices of attachment, we know now.
Hmm.
And
Hmm.
suppose that one of them, say B2,
Hmm.
or yeah, say B2 has more than 3 vertices of attachment,
Hmm.
then means we can show that using pigeonhole principle that they must be skew.
Hmm. Okay, well, there are multiple ways to complete the argument. The way you are suggesting is that, okay, you first deal with the case where one of them is at least 4, but then you have to consider that each of them have exactly 3, and then you again have to do some case analysis. Turns out there is a shorter way to complete the case analysis. Consider that they are not equivalent. Then we will just argue that they have to be skew. Okay, and then we'll deal with the equivalent case. Okay, so let's suppose that b1 and b2 are not equivalent, right? So there are definitely multiple ways of doing the case analysis, but this one is one of the shorter ways of finishing the proof. Okay, so what does it mean to not be equivalent? It means that one of them has a vertex of attachment that is not a vertex of attachment of the other one. Okay, so this implies that one of them, let's say b1, without loss of generality, has a vertex of attachment v such that v is not a vertex of the other bridge. Okay, let me make a drawing. So this is our cycle C. We are assuming that b1 has a vertex of attachment v, and this is not a vertex of attachment of b2, right? In particular, it is not a vertex of b2. Okay, v is not a vertex of b2, but b2 has at least 2 vertices of attachment, right? So what I will do is I will go in both directions and find the first vertex which belongs to b2, right? There will be 2 different vertices because b2 has at least 2 vertices of attachment. Okay, so this is b2. So I'll stop at the first vertex, that is a vertex of attachment of b2, and on this side I will again stop at the first vertex, which is a vertex of attachment of b2. Okay, so let's call them u and w. Okay, let u and w be vertices of attachment of b2 found by traversing the cycle C in both directions, clockwise and anti-clockwise, from the vertex B. Okay, be the first vertices of attachment of B2 found in both directions, clockwise and anti-clockwise. Okay, now look at this segment of the cycle induced by B2. Okay, consider this segment. So let me call this segment P. P is the segment of C induced by B2 such that U, V, and W are all vertices of P. Okay, that is a unambiguous definition if I'm not mistaken. Okay. So if all the vertices of attachment of B1 belong to P, then they would be avoiding each other, right? By definition. So because they are not avoiding each other, they are overlapping bridges. B1 necessarily has a vertex of attachment that is not on this segment. Call it X. And now look at these four vertices U, V, W, X. It proves that B1 and B2 are skew. Okay? Since B1 and B2 overlap, B1 has a vertex X that belongs to the cycle but does not belong to the path P. Okay? And now this implies that B1 and B2 overlap. Sorry, skew are skew. We already knew they are overlapping. We wanted to prove that they are skew. Look at the four vertices U, V, W, and X. Okay? Is everybody happy?
Sir, can you scroll down and show the last line?
Yeah, sure. Okay? Are there any questions or concerns? All right. So if not, then let's look at the other case. Well, if they are not equivalent is done, then the case remaining is when they are equivalent. Right? So case 2 is when B1 and B2 are equivalent. Right? Each of them has at least three vertices of attachment, and the sets are actually the same. The set of attachment vertices of B1 is the same as the set of attachment vertices of B2. Okay? So this implies that B1 and B2 are equivalent K bridges for some K which is greater than equal to 3, because we have already dealt with the case of a 2 bridge. Okay? So if there are at least 4 vertices of attachment, if K is at least 4, let me make a drawing and convince you that we are done. Supposing this is B1, B1 has 4 vertices of attachment, at least 4, there could be 100, and then there is B2, and it has the same vertex of attachment. In particular, these 4 are definitely vertices of attachment of B2. So I'm looking at any 4. And I claim that if I look at any 4, then I'm done. Because I
Yes.
think, yeah, go ahead.
If we assume the set of vertices of attachment to be V1, V2, Vk in a cyclic order,
Right.
then V1, V2, V3, V4 are means if it
Exactly.
yeah.
Exactly. Right. So take V1. So I'll go with the notation that we use in the definition of skew. So for B1, I will take U1 and V1. And for B2, I will take U2 and V2. Right? But you are right. Take any 4 vertices of attachment in any order, and those 4 vertices of attachment, you can fit them to the definition of skewness. Right? Right? So this proves that B1 and B2 are skew. Okay, if K is at least 4, then B1 and B2 are skew. And the point is that consider any 4 vertices of attachment of B1 slash B2. I'm saying slash because they have the same vertices of attachment. Okay, that's it. So the only possibility that we have not dealt with is when k is equal to 3. And this implies that B1 and B2 are equivalent 3 bridges. Good. Any questions or concerns regarding this proof? I think one of the good points about this proof is that you see there are many ways to complete this case analysis. But an elegant proof is one which has the minimum amount of case analysis. That's one way to think about elegance. Because if you have lots of cases, you just is a matter of time to think about how to condense it into as few cases as possible, right? And I think this proof really shows that in a very interesting way. All right. So that is all I want to tell you about the theory of bridges. But now I want to discuss some applications of this theory. Okay. So these are all the, let's say, the basics of Tutte's theory of bridges. I want to also make one small point that Tutte's theory of bridges can also be used to get a polynomial time algorithm for planarity. If you're interested, you can check out the other course I taught, Advanced Graph Algorithms. I think it is around lecture 15. So there we use the theory of bridges to get a polynomial time algorithm to check whether a graph is planar or not. But that's not the that's not really within the scope of this course, so we will not be discussing it here. Okay. All right. So what shall we discuss next? Let's apply this theory to prove interesting results. And the first of them is to show that a three-connected planar graph has a unique planar embedding. Planar embeddings of three-connected okay. So the goal is to use Tutte's theory of bridges let me just write it down as a theorem statement. It's theorem 10.28. It says that every simple three-connected planar graph has a unique planar embedding up to facial isomorphism, right? So what we mean is if you take any two planar embeddings, G1 tilde and G2 tilde, then the faces of G1 tilde and G2 tilde will have the same sets of boundaries. Okay. So how do we show a statement like this? How do we prove something like this? So what is the boundary of a face? Let's call it a facial cycle, right? We know that in a non-separable graph already, if the graph is plane, then every face will be bounded by a cycle. So that will also hold true for simple three connected planar graphs. If you take any planar embedding of such a graph, each face will be bounded by a cycle. Okay? So let G be a simple three connected planar graph. So maybe I'll take a plane graph. I'll take an embedding. Okay? So we know that each face, maybe I'll call it, yeah, I think G is fine. We know that each face of G is bounded by a cycle. Okay? So such cycles will be called the facial cycles of G. Such cycles are called facial cycles of the graph G. Let's take one example. It's my standard favorite three connected planar graph, right? A plane embedding of the graph. So in this graph, how many faces do we have? 1, 2, 3, 4, 5, right? And the boundaries of each of them are the 5 facial cycles of this graph. So this graph G has 5 facial cycles. Okay? But notice that in order to talk about facial cycles, you need faces, which means you need a planar embedding to even talk about facial cycles, right? It is not a graph theoretical or a combinatorial definition. It is related to the embedding. It is in some sense topological.
Sir, I have a question.
Yeah.
So basically, here is the idea something like we will take a facial cycle and we will look the bridges with respect to a particular facial cycle, something like that.
Yes. Yes, we will. Uh-huh.
No, I mean I am just asking the idea.
Yes. Yes, we will relate facial cycles to how many bridges they have actually. So can you check in this graph if you take any facial cycle, how many bridges does it have? Take any facial cycle and count the number of bridges.
I think it will be exactly one bridge.
Exactly one bridge. And now give me a cycle which has at least two bridges. Give me in this graph a cycle that has at least two bridges.
4, 6, 3, 2, 5. The cyclic
4,
form
6, 3, 2,
5.
5, and back to 4. Okay. So let us mark this cycle. 4, 6, 3, 2, 5, and back to 4. Okay. This has two bridges. One is
Just
a
this cycle, this not mean basically this particular cycle is not induced cycle, vertex induced cycle. That's why it has two bridges.
sure, but I don't want to focus on that. I want to focus on the fact that it has two bridges. But you're right. If it is not an induced cycle, there is a chance it will have two bridges, right? Unless your graph is just cycle plus one edge or cycle plus a path. So this case, there is one bridge, 5, 6, that is a trivial bridge. And if you look outside, you have another bridge, the vertex 1 and the three edges incident at 1. Right? So you have a blue bridge and a green bridge. So the point I want to observe is that each facial cycle has precisely one bridge. However, other cycles may have more bridges, as you can see in this example. Okay, good. So now we are talking about how many bridges the cycle has. Does this depend on the embedding?
No, by Euler's formula.
By Euler's formula. Why?
No. What is the question you asked?
The number of bridges. The number of bridges a cycle has, does it depend on the embedding of the graph?
No, it doesn't depend on
It
the.
doesn't. It's a completely graph theoretical or combinatorial concept.
Exactly. Yeah.
Right? Okay, good. So it has nothing to do with Euler's formula. It's just a graph theoretical concept, the concept of a bridge of a cycle. Right? So the number of bridges has no connection, has no relation in some sense to the embedding of that graph, right? Doesn't matter. And that is actually what we will show. We will show that the facial cycles are exactly those cycles of the graph that have precisely one bridge. We'll show that this is an if and only if statement.
Okay, so basically, sir, for any three connected graph G, for any three connected planar
Right.
graph G,
Right.
basically the characterization of facial cycles is basically those cycles having exactly one bridge.
Exactly. Exactly. Okay. Good. So what does it mean to have exactly one bridge? I want to go back to the definition of bridges that we started with in this course, in this module. Let's go back to our example where we defined bridges, right? So we use this 3D model, the bead, string, scissors model, right? And you take a cycle and you cut that cycle out. Every bridge becomes one piece, okay? And this is similar to how we defined separating and non-separating vertices, okay? A separating vertex is a vertex such that you get at least two pieces when you do this scissor cutting thing, okay? In the same sense, we are going to say that a cycle is separating if it has at least two bridges, otherwise it is non-separating. Okay?
So basically, facial cycles they are exactly the separating cycles in the three connected graph.
Exactly. Exactly. A cycle C of a graph G is a separating cycle if the cycle C has at least two bridges. Okay? Otherwise, the cycle is non-separating. Okay? The definition I am using here is slightly different from Bondi Murthy. I think they must have the reasons for using a slightly different definition, but I am not going to use that definition. So, the way they define it, they say that a cycle is non separating if the cycle has no chords, so no trivial bridges, and it has precisely one non trivial bridge. Okay, so they have a slightly more complicated definition. There must be some reason for it that I haven't yet figured out. Okay, but what I want you to prove on your own is that in three connected simple graphs, these two definitions are the same, which is our point of interest. A cycle C, as we defined, is non separating if and only if it is non separating as per Bondi and Murthy, which is the right hand side. Okay, this is for three connected simple.
Basically, when you are saying that C has no chord, that means C has no trivial bridges. Basically,
Yeah. Okay, so this is a do it yourself, and this is the definition of non-separating cycle in Bondimurti. Okay, but it's a very similar definition, right? We are saying it has exactly one bridge. We are not worrying about trivial versus non-trivial. They are saying it has zero trivial bridges and exactly one non-trivial bridge. Okay.
So, sir, I have a question. So,
Yeah,
if
go
we
ahead.
want to, if we indeed want to show that a
Mhm.
facial cycle of a three connected planar graph G is indeed a separating cycle.
Hmm.
Separating cycle, I mean, no, not a separating cycle, is a non-separating cycle. Suppose
Hmm.
I want to show that a facial cycle of a simple three connected planar graph G is
Hmm.
non-separating.
Hmm.
Then basically, what? So, first of all, such a facial cycle cannot be. It must be an induced cycle. It cannot have any chord,
Why?
because if a facial cycle has a chord,
Hmm.
so basically a cycle is a simple closed curve, right?
Yeah.
In a planar embedding, a cycle is basically a simple closed curve.
Yeah.
So if a facial cycle has a chord, then that basically means that face will split into two other faces.
No, that's not clear. So supposing this is
You
my
can
graph.
draw.
Supposing my graph is just this. Okay. This is a facial cycle, but it has a chord. The chord is drawn inside, right? You can't draw the chord in that face because then it will break it into two phases.
No, no,
But
no.
why can't the chord be
Which
drawn
one
in
is
the
the
other?
facial cycle?
Yeah, so 1, 2, 3, 4 is a facial cycle. It has a chord, 2, 4.
Yeah, no, no, no. I am taking bounded face.
Oh, well, why does it matter whether it is bounded or unbounded? I can give you a different drawing. I can give you the drawing like this. You keep going between bounded and unbounded. I've been telling you it doesn't make any difference, right?
Yes, but sir, in this case, which cycle you are taking as facial
1, 2, 3,
cycle?
4. 1, 2, 3, 4 is a facial cycle, but it has a chord which has been drawn outside.
Okay, okay, okay.
Okay. The point is this is not three connected, and that is what needs to come in the proof. So you are actually right. In a three connected graph, this won't happen, but that needs a proof. Okay. All right. Somebody else was saying something at some point. Was it Krishnan? I'm not sure.
No, sir. I was going to
Okay.
say the same thing about drawing the edge outside the cell.
Right. Okay. So we'll prove the following theorem. In a simple three connected plane graph, a cycle C is a facial cycle if and only if C is a non-separating cycle. Okay, we are taking a plane graph, we are taking an embedding because we need an embedding to talk about facial cycles, right? So we are taking an embedding and we are going to argue that the facial cycles which require the embedding to be talked about are the same as the non-separating cycles, which is a completely graph theoretical concept that does not depend on the embedding. Okay, so I am not going to prove this today because we are already at 5:50. The point I want to make is that this implies theorem 10.28. Okay, and the proof is not difficult, so I will put it as a try it yourself, and we will complete the proof tomorrow. All right, but are there any questions regarding why this statement implies the uniqueness of planar embeddings of simple three connected graphs? If that is not clear, then we should discuss it further. All right. So if not, feel free to leave the meeting, right? But I'm here for another 5-10 minutes in case there are any questions or discussions.
Okay, sir. Bye.
Okay, see you.
Bye. Bye. Bye.
Yeah.
So I
Yeah.
had a question.
Yeah,
Means
go ahead.
I don't know if it's a silly question or not, but
Uh-huh.
when are G1 tilde and G2 tilde isomorphic? If I don't know anything about G1 and G2,
Um, by isomorphic, you mean facial isomorphism or graph isomorphism?
facial isomorphism.
Oh, I see. Oh, I see. So you're saying, um, but it seems to me, um, let's see. I have a feeling that for the two embeddings of a graph to be isomorphic facially would imply that the two abstract graphs are also isomorphic, unless I'm
Okay.
missing something.
Means I can't say that. Suppose I don't know anything about G1 and G2, and I get the
Mhm.
isomorphism between G1 tilde and G2 tilde. Then I
Mhm.
want to imply that G1 is isomorphic to G2.
Right, right. So it seems to be true at least for the case of connected graphs because any two faces share an edge, right? So by that you can construct the entire graph G. If I'm not mistaken, if you have the faces, you have the whole graph, right? From the
Correct.
faces you can construct the whole graph,
Okay. Okay. Okay, sir. Yeah. So if
right?
I have the knowledge about the faces of G1 tilde and G2 tilde,
Hmm.
then I can say that they're isomorphic or not, right?
Yeah, I don't see why that would not be the case. Yeah, it seems that the faces, if you know the faces, right, then you will get the whole graph. So the
Yes.
faces of the graph are enough information to construct the entire graph.
Okay, and sir, when I can say that G1 tilde is isomorphic to G2 tilde implies G1 is isomorphic to G2?
Yes, if
It is
I'm not,
always true, right?
yeah, if I'm not missing anything, that seems to be true.
Okay, okay.
Yeah, just verify it, but it seems that that is true.
And sir, another question means I don't know if
Yeah,
it is very silly or not. Means
no, no, go ahead.
suppose G1 and G2 are two k regular graphs.
Okay.
Then when are they isomorphic? If I don't want to form a isomorphism between
Well,
vertices
then
and
this is a
edges.
pretty difficult problem. Graph isomorphism of k regular graphs is, I believe, as difficult as the graph isomorphism problem in general.
Okay, okay.
Yeah, yeah, k regular graphs are a very rich class of graphs. So I don't know if there are any specific results pertaining to that. There might be, but I don't know anything about uh, k regular graphs isomorphism that is very specific to the k regular graphs case.
Okay.
Right? Yeah.
Thank you, sir.
Yeah.
Yeah.
Okay. Okay. You're welcome. All right. Any other questions or concerns? Okay. If not, I'll leave.